Hello and welcome to part 3 of lecture 5. So we've been talking about the span of a collection of vectors, and in this part of the lecture we're going to kind of take a little kind of detour and explain a little bit more fully the vector space of polynomials. So this is something you have seen in Math 1B03 or parts of it, and I just wanted to spend a little bit more time kind of fleshing out this vector space because it's a good source of useful examples that we'll see over and over in this course. So first of all, what is a polynomial? Well, you probably have a good sense of what a polynomial is from calculus. A function going from f to f is a polynomial with coefficients in f if there exist coefficients a0 through am such that your function looks like pz equals a0 plus a1 to the z plus a2z squared up to am times zm. In 1B03, we kind of specialize to the case that these coefficients are all real numbers, but we can extend this so that we can assume that they're complex numbers. And we use the notation PF here to be all polynomials with coefficients in F. Okay, so it's a giant set. It's the set of all the polynomials you can make, okay, with no restrictions on degree. Now, this set PF, you can actually show that it's a subspace of a particular vector space, and it's the subspace of this space right here, f to the power of f. And remember what this means. This is all functions g going from f to f. From calculus, you know that there are a lot of different things that satisfy this last part. It's like the sine function, the exponential function, ln functions, up to worrying about some kind of discontinuities. But the set of all polynomials is a subset of that, and you can actually prove that it has the structure of a subspace. Okay, we won't prove that, but we'll just kind of assume that that fact's true. And the other piece of information that we want to use is the fact that a polynomial has a degree. And again, this is something you would have seen in some of your earlier courses. We say that a polynomial a0 plus a1 to the z1 and so on of this form, where the am is not equal to 0, if it can be written as this form, then the degree of this polynomial is equal to m. So it's the highest exponent appearing in your polynomial. And if the polynomial is 0, then we make the convention that the degree of the 0 polynomial is equal to minus infinity. Okay, so one way this varies from textbook to textbook. Some cases 0 is given every degree, and in this textbook 0 is given degree negative infinity. And once we have this notion of degree, we can define the following set, which we saw in linear algebra 1B03. We can take PMF is all the polynomials of degree m or less. Okay, so this is equal to all polynomials of degree less than or equal to m. Okay. And this is a vector space. Okay, this is a vector space. So we saw in 1B03, this is a vector space. And in fact, we can say something even a little further, is that when we look at this vector space right here, PMF, it's actually equal to the span of the polynomials 1, z squared, up to zm, right? So if this part is true, if this equal sign is true, we actually get then as a consequence that this set of polynomials with degree less than or equal to m is a finite dimensional vector space because we have a finite number of elements that span the whole space. Okay, and the proof is very straightforward. Right? We are trying to show that basically two sets are equal, and the one direction is clear, right? Because span of 1 z up to zm is contained inside of Pm of f. That should be clear because since 1z up to zm is inside of Pf. And what we just proved earlier is that if you have one up to any collection of elements in a vector space and you take the span of them, it will also be in a subspace of the space that you started with. So one direction is okay. Now on the other case, let's say we take an arbitrary polynomial in this set. Well, then that means that Pz looks like A0 plus A1z up to Am to the Zm. And we can rewrite this more concretely as really kind of stressing, elements of our set of polynomials and the coefficients. So we have A0 times 1 plus A1 times Z up to, sorry, not sure why that showed up there. Let me clean that up. Up to Am times Zm. So we have like a coefficient times a polynomial, right? And this is inside of the span of 1 Z up to Zm. So the set of polynomials of degree less than or equal to m is equal to the span of 1z up to Zm. And this is something, again, that you would have seen in Math 1B03, but we're just kind of reinforcing that here. The new thing is, which we didn't really talk about too much in Math 1B03, is the set of all polynomials. And one of the nice interesting things is it gives us a kind of one of our first examples of an infinite dimensional vector space. And here would be a kind of a proof to illustrate how you would prove something's infinite dimensional. The way that you prove it is to kind of do a proof by contradiction. You say, well, suppose that it was finite dimensional, right? Suppose that there were a collection of polynomials, P1 up to Pt, that generated, you took all linear combinations, you could get all the polynomials of any degree. Now what we're going to do is let m equal to the max of the degree of P1z all the way up to the degree of P2z. So look at each of these polynomials, figure out what their degrees are, and let m be the largest degree that appears. Okay. Now what are we going to do with this information? Well, then z raised to the power of m plus 1 is inside of p to the f, because that's just simply a polynomial. It can be a polynomial of any degree. All right. But Zm plus 1 is not in the span of P1z up to P2z, right? And why is this? Since all Piz have degree of the Piz less than or equal to m, and so the degree of any linear combination of these polynomials is going to be less than or equal to m. So in the span on the right-hand side, the largest degree of a polynomial that appears on the right-hand side is m. No matter how you take a linear combination, you can't bump the degree up. On the other hand, on the left-hand side, this set here, there are polynomials of any degree, right? So the two sets can't be equal, okay? So Pf does not equal span of P1z up to Ptz for any finite list of polynomials P1 up to Ptz. Okay. So we kind of used a proof by contradiction, said that if there is equality, then everything on the right-hand side can generate everything on the left-hand side. But on the left-hand side is something of degree m plus 1, and on the right-hand side, everything has degree less than or equal to m. So this gives you kind of a nice example of both a class of vector spaces, and it also gives you kind of your first example of an infinite dimensional vector space. In our last example, we'll look at another example of an infinite dimensional vector space.